Artificial intelligence systems operate on many forms of data. This video introduces the major data types used in AI systems and explains why understanding data structure is essential. Different data types impose different constraints on modeling, storage, computation, and interpretation. Data type matters because it directly influences which algorithms can be used and how systems are designed. A model suitable for numerical tables may be completely inappropriate for text, images, or time-based signals. Structured data is organized into fixed formats such as tables with rows and columns. Each row represents an observation, and each column represents a specific feature with a consistent meaning. Structured data follows a predefined schema. This regularity makes it easy to store, query, and analyze using traditional databases and statistical models. Common examples of structured data include financial transactions, sales records, inventory tables, and sensor readings stored in spreadsheets or relational databases. Unstructured data does not follow a fixed schema. It includes data where structure must be inferred rather than assumed. Text data is a major form of unstructured data. Emails, documents, messages, and social media posts all fall into this category and require specialized processing. Image data consists of pixels arranged in grids. Although images appear intuitive to humans, they are complex numerical arrays to machines. Audio data represents sound waves over time. Speech, music, and environmental sounds are captured as continuous signals that must be transformed for analysis. Video data combines images over time, often with audio. It is computationally expensive and contains multiple layers of information. Semi-structured data lies between structured and unstructured formats. It contains some organization but does not conform to rigid schemas. Examples of semi-structured data include JSON files, XML documents, and system logs, which contain tags or keys but flexible structure. Numerical data represents quantities. It can be continuous, such as temperature, or discrete, such as counts or event totals. Discrete numerical data represents whole values, while continuous data represents measurements along a range. This distinction affects model assumptions. Categorical data represents labels rather than quantities. Examples include colors, product types, or user categories. Ordinal data is categorical but ordered. Ratings such as low, medium, and high have relative ranking but no fixed numerical distance. Temporal data includes a time component. The order of observations matters, and dependencies may exist across time steps. Time series data tracks values over regular intervals. Examples include stock prices, sensor readings, or website traffic. Event data records discrete occurrences, such as clicks, transactions, or system alerts. Timing and frequency are often critical. Streaming data arrives continuously in real time. Processing must often occur with low latency and limited storage. Some datasets are static, meaning they rarely change. Others are dynamic and evolve continuously as new data arrives. Multimodal data combines multiple types, such as text with images or audio with video. These systems require coordinated processing strategies. Each data type introduces constraints. Some models cannot handle missing values, while others cannot process sequences or raw signals. Data types often need to be transformed. Text becomes tokens, images become numerical tensors, and categories become encoded values. How data is represented internally can significantly affect model performance and learning stability. Different data types have different storage requirements. Images and video consume far more space than tabular data. Computational costs also vary. Training models on high-dimensional data requires more memory and processing power. Computational costs also vary. Training models on high-dimensional data requires more memory and processing power. Latency requirements depend on data type and application. Real-time systems impose stricter constraints than offline analysis. In healthcare, AI systems may combine structured records, medical images, and clinical notes within a single pipeline. In banking, structured transaction data dominates, but text and event logs increasingly play important roles. Social media platforms operate primarily on unstructured and multimodal data, requiring scalable processing systems. Choosing the right model depends on matching model assumptions to data properties. A common mistake is applying models without considering whether the data structure supports their assumptions. Treating all data as interchangeable leads to poor system design and unreliable results. Data granularity refers to the level of detail captured. Higher granularity provides more detail but increases complexity. Aggregation can simplify data but may remove important variation or minority patterns. Data formats evolve over time. Schema changes can break pipelines if not managed carefully. Compatibility across systems is a practical challenge when integrating heterogeneous data sources. Clear documentation helps teams understand what data represents and how it should be used. Data catalogs support discovery, governance, and reuse across organizations. Data governance defines who controls data access, modification, and responsibility. Ownership clarifies accountability when errors or misuse occur. Access control protects sensitive data and limits unintended exposure. Security concerns vary by data type, especially for personal or proprietary information. Privacy risks increase as data becomes more detailed or personally identifiable. A practical mindset begins by understanding data types before choosing models or metrics. Asking what type of data you have is often more important than asking which algorithm to use. The key takeaway is that data type shapes every technical and organizational decision in AI. Understanding data types prepares you for effective data collection and pre-processing. Next, we examine how data is collected and generated, and why those choices shape everything that follows.